think that just about covers it as an introduction to generalization. So I think maybe it's a good time to reflect on what we've learned.
I'm willing to do that, especially if it means I don't have to do another quiz.
Okay, well, but okay, no, I'm not going to do another quiz. But I am going to ask you what we learned.
Okay, I think I can remember some of that. So I think the big thing we learned is that there is both a need for and a way to do generalization.
In reinforcement learning, yeah.
And the need part comes from the fact that for a lot of problems we care about, there are zillions and zillions of states.
You could be our generation's Carl Sagan.
Yes, zillions and zillions of states. And that's a problem because, of course, we'll visit states that we've never seen before, and the chances of us seeing every state an infinite number of times and all that other stuff that the theory requires is just kind of unreasonable, or at least slow. So it'd be nice to overcome that.
Good. Okay. And methods for?
You talked about a few methods, but I think at the end of the day, it really boiled down to let's just take all that stuff we learned in supervised learning and apply it.
Cool. But we did talk about some specific ones. Do you remember any particular supervised learning methods that we looked at in the context of generalization and reinforcement learning?
Sure. We looked at linear function approximation, which makes sense because, linear is nice and well-behaved, or at least we hoped it was. And it does seem like the simplest, most straightforward thing to do based on what we know. But I think it's worth mentioning that we were function approximating something in particular, right? So we were deciding to do the value functions and to try to learn those. That's how we were doing our generalization.
Right. That's a good point. We actually looked at different functions that we might approximate: value functions, policies, and models. And we focused primarily on value functions. Models,
Right.
There's interesting things to say about that. But it's not nearly as well studied or as well understood. The value function case, we just focused on representing like the v function or the q function. And that could be done in a number of ways.
Mm-hmm.
And we looked at kind of a general gradient form where we turned the Bellman equation itself into a kind of an error measure. And then we looked specifically at linear value function approximation, how you could, if you have a set of features, you can map them to values using a linear function and how we might learn that linear function.
Right. And that's pretty much what we spent almost all. I don't think we did hardly anything with policy function approximation.
Nope.
And that's okay. And one of the reasons it's okay is because you were able to talk about lots of successes that people have had doing function approximation with value functions.
Yeah, and there's some successes on doing function approximation with policies as well. In fact, a lot of the coolest stuff in robotics in the reinforcement learning setting has happened where there's an actual gradient taken with respect to a representation of the policy. It's not exactly clear why it seems to be the more effective way to use feedback in the robotic setting, but it it's worth noting at least that this is doing policy gradient methods do seem to work well in the robotic setting.
That's a good point, but it doesn't really matter. It's not like robotics is the future or anything.
Robotics is totally the future.
We'll see. We'll have this conversation in 2050 and see what we think.
In 2015, it is 2015.
No, 2050.
Oh, 2050. Oh, phew. I'm like, oh my gosh, it's the future, and I wasn't even paying attention.
Well, that's okay. I, for one, welcome our new robotic overlords.
Oh, good.
In the meantime, we had all these successes, and you named a few, right? The one I remember the most was TD Gammon, but there were others, which if I went back and looked at what we recorded, I'm sure I could find out what they were. Or maybe you'll just remember.
Well, I mentioned several, but Atari is one that actually came up relatively recently, and hopefully will actually change the way that people think about this whole topic of generalization. But we'll see. I mean, it's still too new to know.
Oh, very good, Prince. Okay, so now those successes, of course, were followed by the downer of problems and sort of problem cases where things that seem like they would obviously work do not obviously and easily work, even in the case of linear function approximation.
Yes, that's exactly right. The good news is in the last few years, there's a new set of methods that are based on TD and a gradient, but it's a different kind of gradient that actually uses the function approximator as part of the error metric that's being resolved, and that these can actually, these provably converge. For the case of linear in particular, the paper that talks about GTD2 actually shows what happens when you apply this particular problem case, the Baird counterexample that we looked at, and you can actually correctly learn it if you use this other update rule instead of kind of the classic Bellman residual minimization kind of thing.